Welcome to this explainer. Today we're putting on our detective hats, but we're going way, way underground. We're talking about the hidden, high-stakes science of mudlogging. It's basically CSI, right? But performed thousands of feet beneath the surface. If you've ever wondered how on earth we actually know what's going on down there while a massive drill bit is just blindingly spinning away, well, you're in exactly the right place. We're going to break down the actual forensic methods used to decode the Earth's deepest secrets step by step.
Okay, let's dive into this by looking at the core paradox of drilling. We're trying to recover physical, tangible pieces of rock. Think about it. Nature literally took millions of years to lay these formations down, right? And it costs energy companies immense amounts of time and millions of dollars just to bring tiny, tiny fragments of them back up to the surface. It's this massive, incredibly expensive operation, all focused on retrieving little pieces of evidence.
So, moving on to Section 1, the journey of mud, transporting the evidence. How does that physical evidence actually reach us? Well, in drilling, mud isn't just, dirt and water. It's a highly engineered drilling fluid. And for our purposes as subsurface detectives, this mud is our getaway car, our transport vehicle. It gets pumped all the way down the drill string to the bit, and as that bit crushes the rock, the mud sweeps up those freshly cut rock fragments and carries them all the way back up the annulus. That's the space between the drill pipe and the hole, right up to the surface. But there's a catch here, and it's called lag time. See, when you look at a rock sample at the surface, it wasn't cut a second ago. It was cut whenever that specific volume of mud began its long journey from the bottom. And because the flow rate of the pumps can fluctuate, measuring by time alone, yeah, that's wildly inaccurate. Instead, we measure lag in pump strokes. We know exactly how much mud each stroke of the pump moves, so we just count the strokes to know exactly when our evidence reaches the top.
Now, to calculate that lag accurately, we've got to do a little math. The drill string and the hole itself, they aren't just perfectly uniform tubes. The hole has different sections, like casings and open hole, and the drill string is made up of different diameters of pipe and collars. So the preferred method is this two-step calculation. First, we determine the length and dimensions of each individual section of the annulus to calculate their specific volumes. Then, we just add them all together. Boom! This gives us the exact number of pump strokes needed to bring our sample from the bit straight into the lab.
All right, Section 2, catching the evidence, capturing rock samples. Once we've counted our strokes and our mud has made that long journey to the surface, we have to actually catch the evidence. And guys, we are talking about physically capturing tiny, sometimes half-millimeter pieces of rock out of a rushing river of thick drilling fluid. It's like finding a needle in a flowing haystack. We generally have two ways to do this. The most common method? Using shaker screens. We'll place a bored box at the foot of the screen to collect cuttings through a complete, specific depth interval, say catching a representative sample of 10 feet or 30 feet of rock. But if the shaker screen is being bypassed for some operational reason, we pivot to a settling box. We divert a small part of the mud from the flow line into this box so that heavy rock cuttings settle out. That ensures we literally never miss a piece of the geological puzzle. Now, you obviously can't analyze a rock covered in thick mud, so washing these cuttings is absolutely crucial. And this brilliantly illustrates how the drilling fluid dictates our lab work. If the rig is using a water-based mud, cleaning is usually pretty straightforward. We just gently hose the sample down with a jet of water. But if they're using an oil-based mud, well, that mud is great for the hole because it prevents the rock from sloughing and falling apart, but it is a massive headache for the logger. Water won't clean oil, so we have to use specialized detergents to scrub the cuttings clean. It's basically the most high-stakes load of dirty dishes you'll ever do, but hey, it's the only way to actually see the rock. Which brings us to Section 3, reading the rock record, decoding the Earth. Now that we finally have a clean, wet sample, we enter the core of our investigation. This is where the mudlogger truly acts as the lead detective, sitting down at the microscope, usually under 10-power magnification, to decode exactly what the Earth is trying to tell us. To make sure we don't miss any clues, the industry relies on a strict protocol called the Order of Written Description. Whether we're looking at clastic rocks like sandstone or non-clastic rocks like limestone, we evaluate features in a highly specific sequence, every single time. Color is always first, then texture, things like grain size or crystallinity, then hardness, and so on. Following this standardized order reduces the chance of missing an important property. It increases uniformity among geologists, and crucially, it saves a lot of time when things are moving super fast on the rig. Let's look at that very first feature, color. The color of a wet rock sample under the microscope provides immediate, really powerful clues about the rock's history and environment. For example, green often points to minerals like gluconite or chlorite. Dark gray or black? That can mean carbonaceous material is present. Red or orange modeling usually indicates surface weathering or oxidation. But as a deep earth detective, you really have to watch out for red herrings. Sometimes tiny fragments of the steel drill bit can rust after being caught, creating these false red stains on your sample. Next up is grain texture. We're looking at the size, shape, roundness, and sorting of the grains. This tells us how the sediment was deposited millions of years ago. And there's a very clever, simple forensic tool used here. It's a photographic grid made of half-millimeter squares that is actually fixed right to the bottom of the sample examination tray. It gives the geologist an immediate, built-in scale to measure those tiny, tiny grains against.
Pretty smart, right?
Now, when our eyes aren't enough, we turn to chemistry. The absolute most common chemical evaluation is the 10% hydrochloric acid test. We place the cuttings in a spot plate and add just a drop of acid. If the rock is pure limestone, it will effervesce or fizz violently and immediately. But if it's pure dolomite, it won't react at all in cold acid. You actually have to heat the spot plate up before the dolomite will even start to bubble. It's a fantastic, definitive way to tell two very similar-looking rocks apart. All right, all of this geology is fascinating, but let's move on to Section 4, Hunting for Hydrocarbons, Discovering Oil and Gas. Because ultimately, we are here to discover oil and gas in commercial quantities. We're moving from basic geology to the main events. Which brings us to a critical question. You have a tray of crushed, wet rocks. They've just been pumped up from literally 2 miles underground. So how do we actually spot the oil? How do we know if we've hit the jackpot? Well, we look for 3 main indicators: staining, fluorescence, and cut. Staining is exactly what it sounds like, visible color left by the oil right in the pores of the rock. But, and this is a huge but, high-gravity light oils might leave absolutely no visible stain on the rock surface whatsoever. None. That is why we place every single sample in a UV box. Under ultraviolet light, hydrocarbon fluorescence will actually glow in these beautiful shades of blue, yellow, or gold. But we still aren't done, because, wouldn't you know it, some minerals fluoresce too. So, to be absolutely sure, we have to perform a cut test. The cap test is the definitive proof. We isolate those glowing cuttings in a dish and drop a solvent, like chlorothane, onto them. If it's true hydrocarbon oil, it will visibly leach out of the rock and dissolve into the solvent, streaming out in a yellow or brownish color. We then grade that cut based on how fast it streams out and exactly what color it is. After the solvent evaporates, it leaves behind a ring, and this ring tells us the quality of the oil. Live oil, which is mobile in the reservoir and packed with volatile gas, leaves behind a bright, glowing residual ring. Dead oil, on the other hand, which has little to no gas in solution and is much harder to produce, leaves behind a dark brown or black non-fluorescent ring. Okay, up to this point, our work has been pretty quiet, microscopic lab analysis. But mudlogging isn't just about finding oil. It is about keeping the rig from blowing up. Let's zoom out to the macro scale for Section 5, the dangers of tripping, preventing blowouts. We have a truly dramatic statistic here that completely changes the dynamic of the job. 75% of well kicks, which is an unexpected influx of formation fluid that can lead to a catastrophic blowouts, happen during tripping operations. Tripping simply means pulling the massive drill string out of the hole, what the industry calls pulling out of hole, or POH, or running it back in, known as RIH. It sounds like a completely routine process, but it is incredibly, incredibly dangerous. So why is it so dangerous? Think about displacement. When you're tripping out, or PO, you are removing a massive volume of steel. If you don't replace that volume with mud, the fluid level in the well drops, you lose hydrostatic pressure, and the formation can literally blow out. Conversely, when tripping in, or RIH, the pipe displaces the mud. If the mud doesn't rise exactly as expected, it means fluid is escaping into the formation, or far worse, formation fluid is actively entering the well. Because the margins for error are so incredibly thin here, the mudlogger has to meticulously monitor the trip tank, which measures mud volumes in precise detail. Industry standards dictate very strict rules. You must check the volume every 5 stands of standard drill pipe, every 3 stands of heavyweight pipe, and every single stand of massive drill collars. If the numbers don't perfectly match the calculations and a kick is even suspected, the absolute rule is you never run back to bottom. You shut the well in immediately to prevent disaster.
Which leaves us with this final thought. We started out by looking at tiny fragments of rock under a microscope, hunting for glowing drops of ancient oil. But this entire scientific endeavor is balanced on the razor's edge of extreme physical danger. Millions of dollars and human lives are on the line, all based on a bubbling rock in a spot plate or a fluctuating mud tank. If 75% of well disasters start during a routine trip, how closely are you watching the mud? Thank you so much for joining me for this explainer. I really hope this helped you understand the intense, hidden science of mud logging.